So dear students, in this video lecture we are going to solve another problem in moment distribution. Very simple problem so that you can understand in a better way. So what are the main steps in moment distribution method? The first step is to find fixed end moment. The second step is to find the stiffness value, that is K value. The K is the stiffness. There are two different formulas. One is 4EI by L when the far end is fixed. Another one is 3EI by L when the far end is simply supported. Third step, the distribution factor. We know we consider a joint B, and from B to A, B to C, we calculating the distribution factor for B to A and B to C by using the stiffness value from B to A divided by the summation of stiffness at the joint B to A plus B to C. In this way, we are calculating the distribution factor for a particular joint. Next one, you form the table. The table should be first one, the joint. All the joints should be mentioned here. Next one, member. Next one, distribution factor. Next one, fixed end moment. So next, you find the unbalanced moment at a particular joint B, A and C, and also check whether the joint A is fixed and whether the joint A is simply supported. If A is fixed, that is the meaning of having the fixed end moment value at this joint. But when the joint is simply supported, we have to balance, or we have to make the fixed end moment 0 at the simply supported condition first and then proceed further. So in this problem also we have A support as a fixed, so the fixed end moment value A can be present. At C, there should not have any fixed end moment value, so we should make the fixed end moment value 0 to have the moment at C, because if you have some fixed moment of minus 20, you make plus 20 for balancing at this joint C, so that it will become 0, and we have to carry over this 20 to the intermediate support B as 10, and you have to add this 10 for the calculation also. In the next step, you can add all the fixed moment value plus 10 to get two values, and you check whether the summation of moment at joint B equal to 0. If it is not, find the unbalanced moment and multiply with the distribution factor and present in the table, and just carry over the moment to the nearest fixed end moment, and next add the values to again checking the summation of moment at joint B equal to 0 and further. So this process is repeatedly go on until we get the summation of moment at joint B should be equal to 0, and we should ensure the moment should be 0 at a simply supported condition. We should not have any moment value at the bottom of the calculation at simply supported point. So with this understanding, we can first calculate the fixed end moment, that is M bar AB is equal to minus WL square by 12. So minus W into 4 square by 12. So it is minus 13.33 kilonewton meter, and the M bar BA plus 13.33 kilonewton meter, because it is plus WL square by 12. And the M bar BC, we have a point load with varying distances. So WAB square by L square minus WAB square by L square on left side, and WA square B by L square on the right side. So minus 50 into 2 into 3 divided by 5 square, which is minus 36 kilonewton meter. And next one, M bar CB. So it is plus WA square B by L square. So that 50 into 2 square, here it is 3 square. Okay. 2 square 3 by 5 square, which is 24 kilonewton meter. So next step is to find the stiffness value. So the K value, KB2A, KB2A. So just observe from B to A, it is a fixed support. B to A, it is a fixed support. So it is 4EI by L when the far end is fixed. So the span for A to B or B to A is 4. So EI. So finally we get EI as the stiffness for BA span. Next stiffness for BC. So the far end is simply supported. So it is 3EI by L. So 3 by 5 into EI. So it is 0.6 EI. So these are the stiffness values for the joint B. Okay, next one, distribution factor. Distribution factor for B to A, because B is the joint. So we consider joint B. So B to A, we consider KBA divided by KBA plus KBC, summation of stiffness at the denominator. So KBA is EI divided by EI plus 0.6 EI. EI plus 0.6 EI. So we have 0.63. Okay. Next one, distribution factor for B to C is KBC divided by KBA plus KBC. So numerator it is 0.6 EI divided by EI plus 0.6 EI. So it is 0.37. So if you sum up these values, it will become 1. The summation of distribution factor should be equal to 1. Okay, next step, we are going to make the table, because we find the distribution factor, we have the net fixed end moment values. So next one, form the table. So first one, joint. So we clearly make the table. We have joint A and joint B. Give more space for joint B, because we have to incorporate two members, B to A and B to C. So B to A on left side, because it should be towards A. B to C on the right side, it should be towards C. So this is member. Every row should be lined. Next one, the distribution factor. The distribution factor is here 0.63 B to A, here 0.37, 0.37. Next one, the fixed end moment. Fixed end moment, we can make a line. The fixed end moment value, you have at A it is minus 13.33, B to A okay. You make the table clearly. From A to B it is minus 13.33, B to A it is plus 13.33, B2C is minus 36, C2B is plus 24. So these are the fixed moment value. Initially, all the joints are assumed to be fixed, then only we can get this value. Then we have to release one by one depending upon the support condition. Initially, you consider the support at C, it is a simply supported condition. So it should not have any moment value, but we have 24 at C. So we have to balance this 24. So balance the joint C by considering minus 24. Minus 24. So minus, I am going to balance here minus 24 to make the zero moment here. Next one, if you balance this 24 with minus 24, we have to make carry over to the nearby point, to the nearby point. What are the possible points here? From C to B is the possibility, where B is the intermediate support. It is also considered as a fixed one. Intermediate support is normally considered to be fixed. So the fixed support can have half of the moment, 24 by 2, that is 12. We have to follow the same sign for the value. So minus 24 by 2 is minus 12. Then for our convenience, you again add up all these resultant values. You again add up all the resultant values and you can proceed further. So it will be convenient. Here it is minus 13.33, 13.33, here minus 48, here it becomes 0. So first step, we make the support C moment equal to 0 because of the simple supported condition. Next, A support can have the moment, so no problem. Leave it is minus 13.33 itself. Next, you concentrate on support B. The summation of moment at support B should be equal to 0, but we have the unbalanced moment here. What is the value of unbalanced moment? 13.33 minus 48. So 13.33 minus 48 is the value of minus 34.67. Here we have unbalanced moment of minus 34.67. So we should add plus 34.67 for the joint B. Okay, for the joint B. Next one, this unbalanced moment should be multiplied with this distribution factor 34.67 into 0.63 is equal to 23.22 and 34.67 into 0.37 is 11.44. So we calculated the unbalanced moment 34.67 by adding 13.33 minus 48 at joint B and consider the opposite sign. We get minus 34.67 here. So consider the positive sign 34.67 and multiply with this distribution factor 0.63 and put the value here and multiply 34.67 with 0.37, put the value below the value. Now you add this at this stage. You can add every balancing and carryover stage. Here I missed the carryover step. So once you multiply with the distribution factor, you should carry over to the nearest support, possible support, because the A is the fixed support. So you can carry over here. You can carry over here as 23.22 divided by 2 is 11.665. But here you should not carry over from B to C because C is a simply supported condition. So there is no meaning of carrying over the moment to the simply supported condition because it should be the moment at simply supported condition should be equal to 0. So only possibility is the carry over from B to A. Okay, now it is over. So this step is carry over step. Finally add minus 13.33 plus 11.665 is minus 1.665. Here 13.33 plus 23.22 is 36.55 minus 48 plus 11.44 is minus 36.56. Here you can drop the same value here. Okay, now you consider the equilibrium condition, that is summation of moment at joint B equal to 0. We get this value. Um, uh, we can eliminate very small deviation from these values. 0.001 deviation we can ignore. We can ignore. So the final moment value we get M A to B is the negative moment of 1.665 kilonewton meter, and M B to A we get 36.55 kilonewton meter, and MB to C we get minus 36.55 kilonewton meter, and M at C to B equal to 0. So this is the final moment value. Okay, you can draw the bending moment diagram. You mark the anti-clockwise moment, that is minus 1.665 here, and at joint B to A it is clockwise moment of 36.55, here anti-clockwise moment of 36.55, and at joint C is 0. So you extend the ordinate on the tail side, you connect, and you superimpose the free body bending moment diagram and mark the values. Here the value is WAB by L, which is the value of 60. Here W L square by 8 is the value of 20. So this is the BMD for this problem, and you note how to calculate the reactions from the bending moment value and how to draw the SFD. So we have to complete the problem up to the reactions. So mark the moment 1.665, here 36.56. We have the loading of 10 kilonewton meter per meter, and the support is RA. Here I am naming is RB1. So I am going to find RB1. So taking moment about A equal to 0. So I am considering RB1 because right down is positive. Here right side upward is the present direction of RB1. So minus RB1 into the span 4 meter plus the direction of this moment is opposite to the rotation of RB1. So it is plus 36.56, and also 10 into plus 10 into 4 square by 2, and consider the moment direction here. It is in the direction of RB1, so minus 1.665 equal to 0, and we will get RB1 equal to 28.70 kilonewton. Please check for the correctness. Next one, RA, you will calculate from the total loading minus RB1. So you will get 11.29 kilonewton. So next loading diagram, you consider this is RB2 with a moment value of 36.56. Here the moment is 0, and the support reaction is RC, and the loading is about 50 kilonewton at the distance of 2 meter and 3 meter. I am making the moment equation at B equal to 0. So minus RC into 5 plus 50 into 2 minus 36.56 equal to 0. So that you will get RC value is 12.7 kilonewton, and RB2 you deduct it from the total load 50, 12.7 equal to 37.3 kilonewton. So now we got all the reaction values to draw the shear force diagram. So how to start the shear force diagram? Here you mark RA value, that is 11.29. So here it is a UDL. So at B point you mark RB1, right down is positive, we get only right side upward. So you mark it is on the negative coordinate 28.7. So you connect this, and RB2 is 37. So it is left up. This direction is left up. So it should be marked on the positive ordinate. So mark it is 37.3. Next one, it is a point load. So up to point load, you have to extend this, and um, under the point load. So at C you get the value of 12.7. So mark the ordinate. Up to the point load, it will extend to the same and drop to 50. So 37.3 minus 50 will reach 12.7. So it is S of D. So this problem is a very simple problem in moment distribution because we get the final moment within two iterations. So when sway problem or some other, if you have three span or three members connecting at a joint, you will get more iteration and more repeated balancing and carryover steps. So you take this problem as a example to work out more exercise problems.